Hey friends, welcome back. Now in today's session, we discuss about process synchronization, background, and all of the stuff related to process synchronization such as critical section problem, Peterson solution, synchronization hardware, and semaphores. So let's get started. By process synchronization, we mean that the processes, when they are cooperating with each other, they will be sharing some sort of data, right? So these are the concurrent processes. These are the processes that are running concurrently. So concurrent access of two or more process to the shared data may result in data inconsistency. When two or more process try to share same data at the same time, then the data may be inconsistent. Maintaining data consistency requires mechanism to ensure the orderly execution of cooperating processes. So we need to maintain data consistency to ensure that the cooperating processes get the correct data for their execution. Now suppose that we want to provide a solution to consumer-producer problem. Let us first understand what is consumer-producer problem. So here a consumer consumes an item that is produced by the producer. Unless the producer produces an item, consumer cannot consume it. That is, consumer cannot use the problem. So producer will produce the data items and will put in the shared area or buffer from where the consumer will access the data item. So in order to provide a solution to consumer producer problem that can potentially fill all of the locations in a buffer. See here buffer is shown. So we need to provide a solution to this consumer producer problem. See, if producer doesn't produce any of the data element, the consumer is incapable of accessing the data elements here. And if the producer keep on producing while the consumer is slow in its consumption, then it will overflow from the buffer area. So this is the problem here, and we need to provide a solution to this. So an integer variable labeled as count is used to keep track of the number of filled locations in the buffer. So here buffer is shown, which is having empty spaces right now. We are using a variable labeled as count in order to keep track of the filled locations in the buffer area. Now initially we set the count as 0 to indicate the buffer is empty right now. As soon as the producer produces a new data item and places it in a buffer location, then we increment the count by 1. And this count value is decremented as soon as the consumer consumes an item from the buffer location. The integer variable here in and out are used as indices into the buffer. See here, other than count, we are using two more variables to indicate the indices into the buffer as in and out. Now here is the pseudocode for producer consumer problem that we are discussing right now. See here, in producer code we have these lines of code. Producer produces an item and we are calling it as next produced. So item type next produced. Now producer will be executing a while loop while the condition is true, will keep on producing an item and put it in the next produced. That is the buffer. We are labeling it as next produce. So producer will produce a data item and will put it into the buffer. Now and keep on incrementing the count as soon as it produces a data element. Okay, so while the count is equal to buffer size, now here buffer size matters a lot. The count will keep on incrementing until it equals the buffer size. So producer is able to produce those many data elements till the buffer is full. So while the count is equal to buffer size, do nothing. The producer, if the count is equal to buffer size, then no new data elements can be produced by the producer. Buffer in is equal to next produced and in is equals to n plus 1. So your buffer in, so here you are putting the data element that is produced into the buffer into the buffer location indicated by in variable here, and this variable we are incrementing so that it can point to the next location in the buffer, and simultaneously we are incrementing the count integer to keep track of the data elements produced. And here is an end of while loop. Now the buffer size in this case we are keeping it as 10. So it is hash defined buffer size 10. Now we are using a construct here type def structure which is producing an item. So item buffer, here we are declaring buffer of type item and it is of size 10. We are initializing all the variables here in, out and count initially as 0. Now let us have a look at consumer code. Again here consumer is using the same data type here item which is of type structure, and next consume is of type item. Now while the condition is true again and while count is equals to 0, then nothing can be done. If count is 0, that means no data element exists in the buffer, it is empty. Next consume is equal to buffer out. Now here we are using out variable to take out an element from the buffer. Okay, and out is equals to out plus 1% buffer size. So here we are again changing the value of out variable to this value. That means whatever out plus 1 divided by buffer size, whatever is the remainder will be assigned to out variable. And we are decrementing count by 1. Since an item is consumed by the consumer, we will decrement the count variable. And there is an end of while loop. I assume that you have understood this code. Okay. Now there is another point to discuss here is race condition. The producer and consumer code segments are correct when each runs sequentially. They may not function correctly when executed concurrently. Just now the code we have seen, producer as well as consumer, these codes are correct if they run independently, or if they run one after another, then the code is correct, absolutely correct. But if these codes run concurrently, they may not function correctly. They may not execute properly and give you the correct result. They may result in data inconsistency, I mean. Since here, now how they can result in data consistency, let us see. Here we have count incremented. So count plus plus could be implemented as a sequence of code here. Obviously internal registers are utilized here. So count value is initialized as register 1. Then to increment the count value, we are actually incrementing the register value by 1, and then the incremented value is assigned to count here. See, register 1 is equals to count, then register 1 is equals to register 1 plus 1, and then this updated value is assigned again to count. So this particular single line of code has three things to be done at the background. Similarly, count decrement C minus minus can be implemented in these three lines of code. So here we will be using register 2, initializing it, and then decrementing the register value, and then updating the count by assigning the decremented register value here. Now, one execution may interleave the above statements in an arbitrary order when count initially is 5. Now, let us examine a situation where this count value may not be correct. It may result in inconsistent value. See here, at time 0, the producer executes register 1 is equals to count. So register 1 right now, if count is equals to 5, so register 1 will be assigned a value of 5. At time t1, the producer executes register 1 is equals to register 1 plus 1. So here register 1 now has an incremented value. 5 plus 1 is 6. So this is 6 here. At time 2, consumer executes register 2 is equals to count. See, at time 0, whereas register 1 value is 6 here, at time 0, register 2 value is assigned as 5. Because count value is same, we haven't incremented count value yet. Then at time T3, consumer executes register 2 is equals to register 2 minus 1. So register 2 will be now 4, a decremented value, a decrement by 1. That is 5 minus 1 is 4 here. Now at time T4, producer executes count is equals to register 1. Since register 1 value is 6, so count will be given a value 6. And at time T5, consumer executes count is equals to register 2. And right now here we have register 2 as 4. So count value will be assigned a 4 here. Now see, at this time we are having count value as 6 and now count value as 4. Now this results in incorrect state of this counter value, that is 4. So if count is equals to 4, it indicates that 4 locations are full in buffer, where in fact 5 locations are full. Are you able to understand this? So this results in inconsistent data, indicating that counter, we are using a count integer variable to keep track of the filled locations in buffer. So if count is equals to 4, this means that 4 locations are filled in the buffer, whereas actually 5 locations are full. So this is incorrect value. Now a race condition has occurred. Since we are getting inconsistent value, a race condition has occurred here. This means that several processes are able to access and manipulate the same data concurrently. Now, what do we mean by race condition? This is a situation where many processes are able to access as well as manipulate the same data element simultaneously. At the same time, they are able to access the same sort of data and they can even manipulate its value. The outcome of the execution depends on the particular order in which the data access and manipulation takes place here. What result you will be getting after this race condition depends on the execution of the order in which the data access and manipulation occurs. Now, to guard against this race condition, to avoid this race condition, we need to guarantee that only one process at a time can manipulate the shared data variable. So in this case, just the example that we have discussed here, in this case, the shared variable is the counter variable. So we need to make sure that only one process at a time, among the cooperating processes, only one process at a time is able to manipulate the counter variable in order to avoid race condition. Next point of discussion is critical section problem. Let us assume that the system consists of n processes, in which each process has a segment of code called a critical section. Assuming that you are having n number of processes. Now n can take any value, any integer value within limit, that is, it does not tend to infinity. So let us assume that you are having 5 processes, for instance. So each of these processes has a segment of code called a critical section. It is having a segment of code called as critical section. Now in this critical section, the process may change a common variable, update the table, write to a file, and so on. So these are the operations that can be done on in critical section. So every process is having its own critical section, which is manipulating the common variables, the file shared among the cooperating processes, or it can update a table which is shared among the processes. So here, when one process is updating in its critical section, this means that when one process is executing the code of its critical section, then no other process can be allowed to execute in its critical section. If we allow other process to execute their critical section at the same time, then it will result into race condition. So here we apply a binding that when one process is executing in its critical section, there must not be any other process which is executing in its critical section. This means that no two processes may execute their critical section concurrently. Now the critical section problem is to design a protocol that the processes can use to cooperate in manipulating common data. Here we design the critical section to design a protocol, to design a rule that the processes can use to cooperate in manipulating and updating the common data. Here right now we have discussed the critical section problem. If one of the processes is executing in its critical section, there must not be any other process which is executing in their critical section. Right? Now a solution to this critical section is to use 3 code sections here. Code section, first is entry section, then critical section, and remainder section. Now entry section contains the code where each process requests permission to enter in its critical section, and this code can be run concurrently, right? So this is actually the entry point where a code is written, where each process first request for the permission to take entry in its critical section. And here we do not have any problem. There can be many processes which may request a permission to enter their critical section. So hence it can be run concurrently. Next is critical section that contains the code for data manipulation. This code is only allowed to run exclusively for one process at a time. So here this is very sensitive code. Here data manipulation occurs. Hence we cannot allow more than one process to run their critical section at the same time. And the last one is remainder section that contains any remaining code that can execute concurrently. So here are the three code sections